Well, for the past several weeks, we've been talking a lot about integration, and now we're about to embark on something completely new, and that's known as Taylor series. So this is section 10.1 of the text. Now, the origins of the ideas in this chapter really go back to Calculus 1 and the tangent line. So let's just recall the point-slope form of the equation of a line. If we have a line whose slope is m, and if the line passes through the point x0, y0, then the point-slope formula for the line is y minus y0 equals m times x minus x0. And if I add y0 to the other side, I get y equals y0 plus m times x minus x0. So this is the point-slope formula for a line. Of course, many of us are also used to the slope-intercept form, y equals mx plus b. But in calculus, we actually emphasize the point-slope form for the following reason, and that is the tangent line. If we want the equation of the tangent line to a curve at a particular point, we find the slope by using the derivative. So if we want the tangent line at x equals a, the slope is f prime of a, our x naught value is a, and our known y value is f of a. So think about a is x0, f of a is y0 in this above formula. If I plug everything in, I get y equals f of a plus f prime of a times x minus a. This is the standard equation of the tangent line. And we use the point slope because we usually have a slope given by the derivative in a point. So in Calculus 1, we try to wean students off of slope-intercept. Let's take a look at an example. Suppose we have the function f of x equals the natural log of x plus 2, and we'll focus on a equals 3. Let's find the equation of the tangent line to f at 3. If we plug 3 into f, we get the natural log of 5, which I'll approximate as 1.61. If we want f prime, taking the derivative of the natural log of x plus 2 is 1 over x plus 2. If we plug a into that, or plug 3 into that, we get 1/5. So that means the equation of the tangent line at x equals 3 is f of a plus f prime of a times x minus a, and a is 3, so we get the 1.61 plus 1/5 times x minus 3. The tangent line is the best line that approximates f near x equals 3. Here's a graph. This is the tangent line, which is red, at least on my computer, and f of x is in black. I can use the tangent line to approximate the function near x equals 3 because the graphs are so close to one another. For example, the natural log of 3, if I look at f of 3.2, that's the natural log of 5.2, using the formula for f. That works out to be about 1.6487. If I plug 3.2 into the tangent line I just computed, I have 1.61 plus 1/5 3.2 minus 3. That works out to be about 1.6494. And again, what I'm using is this tangent line formula that we just computed. So f is well approximated by the tangent line if the inputs are close to 3. If I go way out here to 6, I can see there's a noticeable difference between the tangent line and the function. And if I try to use the tangent line to approximate the function out there, it just doesn't work as well. F of 6 would be the natural log of 8. That's because of the formula for f. It's the natural log of x plus 2. That's about 2.0794. If we plug 6 into the tangent line, which we had on the previous page, we have 1.61 plus 1/5 times 8 minus 3. And that works out to be about 2.2094. So we can see that if an input is close to 3, the tangent line does a much better job of approximating function, whereas if we plug a point in way over here, pretty far away from 3, we don't get a very good approximation. Now that's Calculus 1, the tangent line. What we're going to be doing in the next couple days is looking at better and better approximations. So we're going to start with the tangent line, and we're going to construct what's known as a quadratic approximation, a degree 2 approximation. We're going to take the tangent line formula from before, f of a plus f prime of a times x minus a plus c times x minus a squared, And we want to find the value of c that gives us the best quadratic approximation. Well, we need to take this tangent line and we need to bend it somehow so that it bends in the same way the function does at x equals a. So if I go back and look at my example, my tangent line was straight, but what I want to do is I want to take this tangent line and modify it to get a parabola which approximates the function f better. I want the function f to bend the same way that I bend that tangent line, so I want the quadratic approximation to have the same concavity as the function does at a, because the concavity measures the way a function bends. So let's take this quadratic approximation, figure out its second derivative, and then match that up with the second derivative of the function f. If I take the first derivative, keep in mind that f of a and f prime of a are just numbers. If I take the first derivative, I get 0 from that. If I take the first derivative of that, I just get f prime of a. And if I take the derivative of this, I bring the 2 down in front, times c times x minus a to the first by the chain rule. So that's the first derivative. So I have f prime of a 2c times x minus 2c times a. Now f prime of a is a number, c is a number, c times a is a number. If I take the second derivative of q, in other words, I take the derivative of q prime, I get 2c. So we want the second derivative of q at a, which is 2c, we want it to equal the second derivative of f at a. And again, here's the reason. We're trying to create a parabola which bends in exactly the same way the original function does near x equals a. So this is the standard formula for the quadratic approximation. It's f of a plus f prime of a times x minus a. All of this is the tangent line. And then we add to it f double prime of a over 2 times x minus a squared. Let's go back and take a look at the same example from before, the natural log of x plus 2, and let's focus on a equals 3. We saw from a couple pages ago that f of 3 was 1.61 and f prime of 3 was 1.5. The first derivative of f was 1 over x plus 2, which I can write as x plus 2 to the negative 1 power. If I take the derivative of this, I bring the minus down in front, x plus 2 to the minus 2. If I substitute 3 into this, I get minus 5 quantity to the negative 2, which is minus 1/25. So the quadratic approximation at 3 is f of 3 plus f prime of 3 times x minus 3 plus f double prime of 3 over 2 times x minus 3 squared. We've computed all the values, we just plug them in. F of 3 is 1.61, f prime of 3 was 1/5, and f double prime of 3 over 2 is minus 1/25 divided by 2, which is minus 1/50. So this is the best quadratic approximation of this function near 3. Of course, if we used a point different than 3, like 5, we'd get a completely different quadratic approximation down here. So what I've done is I've graphed the tangent line up here, the original function right here, and then the quadratic approximation. It's a parabola, and it would actually be a parabola opening down because this is negative. And we can sort of see that the quadratic approximation, because it's concave down, it is going to bend down eventually. If I plug 6 into the function, which I did a couple pages ago, I get 2.0794. If I plug 6 into the tangent line, I get 2.2094. These are not really that close. But if I plug 6 into the quadratic approximation, I get 2.0294. That is closer to the output of f than was the tangent line, and we can see that in the picture above. The quadratic approximation hugs the curve better near 3 than does the tangent line approximation. What I would like for you to do in preparation for class Look at the function e to the x. Look at a equals 0. Find the quadratic approximation at 0. Cosine of x, a equals 0. Find the quadratic approximation. Then do the same thing for x times the natural log of x at a equals 1. Find the quadratic approximation. Now, check. Once you've computed your quadratic approximations, make sure that they are actually parabolas. You can graph them if you want. Okay? So do that in preparation for the next class.